Hello students, welcome back. So another session for you in the physics with another new and interesting topic, work, energy, power and circular motion. Alright, so I guess in the last class, Newton's laws and friction, you guys were a little bit more aware about the mechanics topics and we solved few questions about the Newton's laws and the friction. Alright. So in this sequence, we'll continue with the next topic, work, energy, power. Without wasting any time, we'll proceed further. Okay. So as we see, as per the analysis, I see that in past 5-6 years, let's say, the weightage of this chapter was quite high. 3 to 4 questions were there. In the recent exams, it was 2 to 3, let's say 2 to 3 approximately. So we cannot predict what will be the weightage of this chapter in the coming exam. Assume that it would be somewhere from 2 to 4 questions. Okay, so it's very important we practice sufficient number of problems on this chapter. Work energy only requires practice of specific problems. Okay, so I have handpicked again a few important questions of this chapter which we are going to discuss. So stay tuned and take out your pen and paper. I'll suggest take out your pen and paper and try as I solve the questions here as we discuss the questions. Okay, all right, fine. So let's continue with the work done. You guys all know in the chapter of work, energy, power, what is the outline of this chapter? First of all, we start with discussing the work done, right? Work done by different kind of forces, work done by constant forces, work done by variable forces. Then we proceed towards the energy. Now, energy in mechanics, we discuss mechanical energy of two types, which is the kinetic energy and the potential energy. And then we proceed towards discussing the work energy principle, the conservation of energy. And then in the last, we are going to discuss the power of the force which is doing work. And then the last part is circular motion and vertical circular motion. So that will be the outline. You guys know, you guys are very well aware about this thing. Let's continue without any further ado with the topic work done. All right. So I guess you all know whenever a force is acting, in the last class we said force can change the acceleration, force can produce the acceleration, it can change the state of the motion, it can change the velocity, it can set a body which is at rest into the motion. So force can do that, correct? But how? Force does it, but how? So for this, we require some energy. Without energy, we cannot do anything, correct or not? As most of you guys will be aware that what is energy? Energy is something which gives us the capacity to do work, correct or not? Who does the work? The source or the person or the agent which applies the force. That agent or that source is going to do work and thus it has to spend some energy. So it is all related. Everything is related. Force, work, velocity and everything. They are all related. Okay, all right. So work done. So what is work done? In simpler terms, if I say that work done is simply the product of force and the displacement, since both of them are vector quantities. So what kind of product? Work done is a scalar quantity, so the product has to be a dot product. And you all know how to expand dot product. We put cos theta, where theta is the angle between the force and the displacement, correct or not? Alright guys, now if I write this sentence, you must remember that this is not always true. You should keep in mind that this is only true when the force remains constant throughout the displacement. Force is constant. If it is constant, we are good to go with the formula. It will be simply Fs cos theta. Okay? Please pardon the little bit hiccups in the between. All right. Next thing, when the force is not constant, the force is variable. Force varies with time or with displacement, with distance. Force is variable, then I cannot use this formula. Then you all know that the integration will appear F dot ds. ठीक है, integration of force over a very little displacement. So over a very little displacement, force won't change much, but over large distances, it is going to change substantially. ठीक है, initial to final, like this. Initial displacement to final one, and this is how we are going to proceed. Now see, a very important point. As we just saw the formula that work done is the integration of FDS. Now if somebody plots the graph of force versus displacement, then it definitely tells us that work done is the area under the graph. So I am going to write it down here. Area under force and displacement graph gives the work done by the force. And now these three things we are going to use to solve some important problems of work done. So let's proceed and be focused. Okay, only thing in the chapters in mechanics is be focused as how do I solve the problem, and you just need to reciprocate it. That's it. Alright, so here they have given for the force, they have given that it is 3I cap plus 4j cap. It's a vector quantity, good enough, and it's a constant force, very nice. They are saying that it acts on a body and the body moves from this initial position, I'll write this as initial position vector, to this final position. This is the final position. Find out the work done in this case. So be careful that whenever the positions are mentioned, you need to just recall what is the displacement. Displacement is simply the change in position. So final position vector minus the initial position vector, you get the displacement. So first step is get the displacement, and it's the constant force. So displacement will be final is 4I cap plus 7j cap minus the initial is 2I cap plus 3j cap. So 4 minus 2, 2I cap, 7 minus 3, 4j cap. So this is our net displacement, and we always need the displacement. Okay, if the force is constant, you just need the displacement. You need not worry what is the path taken. Here it's not dependent, or we need not worry about path. Okay, only when what? Again and again I am repeating this thing, so you have to take care that the force is constant. Okay, the work done. The work done will be F dot ds, F dot s, 3I cap plus 4j cap dot with 2I cap plus 4j cap. I guess you guys all know how do we do the dot product of the two vectors. If it is the dot product, the resulting quantity is a scalar quantity, then you just multiply the I cap terms together. So 3 into 2, 6. And then 4 into 4, the j cap together, put a plus sign. That's it. J cap is 1 and I cap is 1. So this is how we solve the dot product. So 3 into 2 is 6, and this is 16, 22. And since everything they have not mentioned, I'll mention that everything is in SI units. This is in meters, this is in meters, and this is in newtons. So the work done will be in joules. This is how you do the problems. Just be careful. It was quite an easier problem on, if I say ki it's just an introductory problem, so it was on the easier side. But just follow the method ki, are we doing everything and each and every step correctly or not? That's it. Okay, next one. In which of the following figures, the work done by the force F in displacing the object through the displacement d is positive? So these are the important terms mentioned in the problem. I have highlighted it. Work done we have to check, and I know that if they have not mentioned anything, force is a constant here. Force is constant. Force and displacement have some angle, so I need to remember the work done formula was F dot S. ठीक है? Okay. F dot S or Fs cos of angle theta between them. They are mentioning कि the work done has to be positive. Force, the magnitude, displacement, the magnitude. Only thing is cos theta. Cos theta will be positive. Cos theta will be positive if the angle is acute. Cos theta will be negative if the angle is obtuse. And so on. Right now we just focus on the acute and obtuse. Okay. So I have to find which one gives me the positive work. I guess most of you would have gotten the answer by now. Let's just check. First one, the angle is 90 degrees. So cos 90 will be 0. Okay. Cos theta will be 0. Work done is 0. Check. In this one, it's obtuse angle. So I know कि cos theta will be negative. Let's change this shade. Cos theta will be negative. So again, this is not the correct one. Here it is 180 degrees, right? They are exactly opposite. So again, the cos 180 will be minus 1, and which is negative. Negative work. While here I see that cos theta will be positive at this angle because it's an acute angle. So this one gives me positive work. So our answer would be option number B. Okay, this is how you quickly check. Alright, let's proceed on to the further little bit more important and more challenging problems where they are discussing variable force. So variable force means what? We have mentioned the formula ki work done is F dot ds या F dx because the displacement will be in the x direction now. So I can simply put F dx. ठीक है? Or Fx dx is also good to say. ठीक है? Now what? I know the formula, now what do I do? What do I think? What should be my next step? So your first step is, whenever I see integration, what pops in my mind is, this is a variable x. What is it? A variable x, correct? And whatever is written in front of dx must be a function of x. So I need to just pull out that information from the problem. Ki is the force a function of x? Function of x. Function of x means it's just an expression of x. So here in the question they have mentioned ki force is 0.1 times x. That means it is definitely proportional to x. It depends upon x. Good to go. Now we can proceed with the integration. So I'll write the work done here. I found the force as a function of x, 0.1 into x, and everything is in SI units, okay? Alright. Now here you just need to see this x dx. So pull the 0.1 outside, and it's simply the integration of x dx, where they have mentioned ki x is going from 20 meters to 30 meters. So I'll put the limits here. This is your definite integration, putting the limits 20 to 30. So this is 0.1 times, and integration of x dx is x square by 2. Okay, this one is the multiplication sign, don't get confused. Okay, x square by 2. So put the limits 20 to 30, 0.1, let's leave it here. So 30 square will be 900 by 2, and 20 square will be 400 by 2. So that is your 500. So 0.1 into 500 by 2, which is nothing but 0.1 into 500 is 50. So 50 by 2 is 25. Okay. All right. Did we make? Okay. Wait. They have mentioned ki the final kinetic energy, and we have just found the work done. Let me just move it aside. So we'll find the final kinetic energy, not an issue. We just need to apply work energy principle. So either what we could have done is get the acceleration and then get the velocity by using the differentiation integration, same process, but I have found the work done, then also not an issue. And they are saying ki it's the retarding force, so we should have put minus sign here. The work done will be negative, all right. The retarding force, and the object was moving with 10 meter per second, the initial velocity. So I'll write the work energy principle that work done is delta K, and the work done we have found is 25. The final kinetic energy they are asking, K final minus the initial kinetic energy. So initial will be, the speed is given, the mass is given. So half mv square. Okay. So K final, take the half mv square on the other side. So K final will be minus 25 and plus half mv square. The mass is given as 10 and the v is given as, that is also 10. So it is 100. So minus 25 and 1000 by 2 is 500. So that is 475 joules. That is our final kinetic energy. If they just ask the work done, so that would have been the problem. Okay? That's the final thing we found, the work done, but the extra thing they found, the final kinetic energy, so it will be the D option. Alright, fine. So let's proceed. So here we did two things. We found the work done as well as we applied the work energy. We'll discuss more about this work energy. So for now you can just proceed, or you can just understand this work done part. This thing we are going to discuss little bit more later on. Alright, fine. Next problem, okay. So this one is again a similar problem, and it is just asking the work done, unlike the previous problem. So here the work done, again the force is variable, so work done will be Fdx, correct? Work done is Fdx, alright. And again they are saying ki it's going from x0 to x1, great, not an issue. So remember that f should be a function of x, and they have given it as a function of x. So I'll keep it here, 3x square plus 2x and minus 10 and dx, and it is going from 0 to 1, okay. Whenever such kind of expression comes in the integration, I hope you all know, if it is separated by plus or minus sign, then you can just separate the integration also. So it will be integration of 3x square dx, okay, and then put a plus sign, integration of 2x dx, and then again put the negative sign, minus 10 times dx. So this is our integration broken into 3 parts, and for all of them the limits will go from 0 to 1, 0 to 1, 0 to 1. Okay. Do the first part, 3x square, integration will be 3 into x cube by 3. Pardon this multiplication sign because it looks like x only, so I'll remove it. So x square becomes x cube by 3, great, 0 to 1. 2x becomes 2 times x square by 2, again 0 to 1, and minus 10 dx becomes 10x, again 0 to 1. So first put the upper limit, and 3 gets cancelled, so it is just 1. 2 gets cancelled, again it's just 1, and again minus 1, so minus 10. If I put the 0, 0, 0, then it is simply 0, 0, 0. So this final answer will be 2 and minus 10, that is minus 8 joules. Tick. Last option. Work done can come to be negative for a variable force, because this force, I don't know ki if it is constant only, or if it is increasing only or it is decreasing. Here it was a plus sign, and with this x increasing, 0 to 1 the x is increasing. So these two parts are increasing, not an issue. But this minus 10, so I don't know ki overall value will be positive or negative. Might happen for a small x, this overall force is negative. So our work is coming out to be negative. It's not an issue. It can come to be negative, which is the option here. Alright, let's proceed to the next one. I hope you guys understood. And wherever if you guys lag behind or you need to go through it once more, just pause this screen and then you can come back, okay? Next one. The work slide, if you remember, I wrote 3 things. कि if the force is constant, then it is simply the dot product. If the force is variable, then it is the integration. And the last part was कि if we have been given the graph of force versus displacement, then work done is simply the area under the graph. So that's what this problem asks. Okay. So position dependent force, okay, force dependent on the position acting on the particle. So force versus position graph is given. Great. They are saying the work done on the particle when its displacement 0 to 5. So the situation is that it's going from x equals to 0 to x equals to 5, like this. So from here 0 till 5, that's the problem. And overall the work done we need to find, so not an issue. I guess most of you would have already gotten the answer. You guys very well know what we have to do. The upper area positive, lower area negative. And to quickly solve it, just remember, mark the base. This base is 1 unit length, this 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 is 1 unit length. The height is 10 and here also the height is 10. So I need not calculate overall answer as it is. I'll just apply this trick. What trick? If you see that this triangle and this triangle are congruent, not just similar, they are definitely similar, but they are congruent, their area is going to be same. If their area is same, then this area and this area will get cancelled. Okay. Look at this rectangle. The base is 1 unit and the height is 10. And here also the rectangle, the base is 1 unit, height is 10. So the area of this rectangle and this rectangle will also get cancelled. I need not even calculate. So what remains is this. Only this one rectangle, sorry, only this one triangle I need to find, and that will be my work done. This and this gets conveniently cancelled, not an issue. So the work done will be the area of this little triangle, half into base into height. Base is 1 and height is 10, 5 joules. Okay, that easy. Straightforward, you get the answer. So again, it's your perspective, it's your option key. How do you proceed? What strikes first in your mind? And that's how you proceed. But always try to simplify the problem first before increasing the calculation. Okay, I need to always do minimal calculation as possible. Check. Now, there was a problem which was discussing the work energy theorem. Okay, now let's discuss what is work energy theorem. They say to do work, energy is required. Definitely the energy is required. That's the aspect of the person who is doing the work, who is applying the force. But what about the object on which the force is being applied? What happens to it? So that thing is discussed by the work energy principle. They say if you are applying a force, if you are doing work, then the object on which you are doing work gains some energy. Gains the energy in the form of kinetic energy. Maybe its potential energy is also playing some role, but again it's fine, it's dependent upon the force. So more or less, I say whenever work is done, the kinetic energy of the body is going to change. That thing is discussed by the work energy principle. Let's look at this statement. They say that the work done by all the forces, the work done by all the forces acting on the body is equal to the net change in kinetic energy of the body. So if I say the work done by all the forces, including the conservative force and non-conservative force, any sort of force, if it is there, I need to take it into account. I cannot skip even a single force here. Take. Delta K is your change in kinetic energy. We cannot skip a little force, otherwise this equation will not hold true. Okay. All right, fine. Okay. Now, the work done and the work energy principle is very important in which scenarios, or how do I know where to apply it? This is the most common question by most of our students. They always ask, sir, How do I know ki whether to apply conservation of energy principle or whether to apply work energy principle? How do I decide it, or how do we proceed in this or in such kind of scenarios? So my only suggestion is, if you don't know ki is the energy is conserved or not, or you cannot figure out ki are there any non-conservative or forces which result in heat loss, if you cannot figure out, then go with the work energy. And in the work energy, your only job is to figure out what forces are acting on the object. If you can get all the possible forces, any force, whether they are mentioned or they are not mentioned, if you can figure out all the forces, then you are always good to go with work energy principle without any second thought. You need not worry ki is the energy conserved or not. I don't care. We always apply the work energy. So go with it. Okay? Now, this was about ki how do I decide whether to apply it or not. Next thing is ki do I need to apply it? In what problems do I apply work energy, and in what problems I think of something else? Because this is work chapter, so I know the questions will be related to work energy only, nothing else. In your NEET exam or in any other competitive exam, final exam, it will be a full syllabus paper, correct? And in full syllabus, you will not get the hint ki whether to apply work energy or kinematics or whatever. Okay? In those scenarios, you can always apply the work energy principle if mass is mentioned somewhere or if force is mentioned anyhow. You will see the velocity, you will see the displacement. They might be talking about kinetic energy, but if mass is mentioned, force is given, then I'll suggest ki go with the work energy rather than thinking about the kinematics. Check. And in almost all of these scenarios, which can be solved with kinematics, can easily be solved with work energy in lesser steps. Again, if the mass is given and if the forces are mentioned in the problem, then only. Okay, so this is how you decide. Fine. So let's proceed with some problems and let's find out ki how to apply work energy, how to use the work energy principle in the problems. Okay. They have said a particle of mass 3 kg, right, moving along the x-axis, position at time t is given by this function. So I'll rewrite the function here. X is 2t square plus 5. Now, dear students, at first I think that I don't know what kind of function is this. Is it a constant acceleration motion? Is it this? Is it that? Do I apply work energy? Do I apply kinematics? Nothing. Okay? Nothing. Now check what other information is given. Have they given mass? Yes, they have given mass. Then definitely I can take help of work energy. Are they asking about work done? So definitely the work energy I need to apply. And they are asking ki time interval 0 to t. 0 to 3 seconds. The t is 3 seconds. There are 3 ways to solve this problem. Straightforward. Okay? Either you use this thing and get the acceleration which will help you get the force, because mass into acceleration is force. First method. I'll write it here. And then I'll tell you which one can be the fastest. Although all 3 methods are almost same, not an issue. Okay. So first method is you get the acceleration, you differentiate it twice, d2x by dt2. Double differentiation. If I differentiate it once, I'll get 4t. If I differentiate it twice, I'll get 4. The acceleration shall be 4. It shall be 4 meter per second square. That's it. I got the acceleration. Using the mass, I get the force. And force is coming out to be a constant one. So 3 into 4, 12 newtons. That's it. If I got the force, they're asking from the interval 0 to 3, so I'll get the displacement. At x equals to, at t is equals to 0, the x initial will be 5. And at t is equals to 3, X will be, this will be 9 and this is 2, so 18 plus 5 is 23. Okay? That's it. Okay? Alright. Now, see, I got the initial position, I got the final position. Now, only thing is I need to get the displacement, which is final minus initial, and that shall be 18 only meters. So, I got the displacement, I got the force. Luckily, the force was constant, so work done is force into displacement. So, 18 into 12. First method. Next method. Next method is, I don't differentiate it twice. Okay? I find the velocity. Differentiate it only once. So this will be 40. That's it. The 5 differentiation is 0. It's a constant number. Okay. I got the velocity. Find the initial velocity at t0, which is putting 0. It's 0 only. Find the final velocity at t is equals to 3, which is 12. Right? From this, if you got the velocity, can you find the change in kinetic energy? The final minus initial. Half m v final is square minus v initial is square. Yes, definitely the mass is given. The mass is 3. V final is 12. So it is 144 and the v initial is 0. Tick. And this will be 72. So 72 into 3. This is 6. And this will be 216. Okay. That would also have been 216. We can calculate it. So this is the second method. Now try to understand why the second method here is crucial, or let's say why are we discussing it. See here, I just found the change in kinetic energy. Were they asking me change in kinetic energy or the work done? They were asking the work done. What did we study just before? Work energy principle, which says that if you get the kinetic energy, then you can find the work done by all the forces. And here only one force was acting on it. Okay? Oh, sorry. Whatever forces, I don't know what forces, the net displacement was given and they are asking the work done by all the forces, whatever be it. So here I found the net force and it will give me the work done by all the forces. Here I found the delta K, which will be equals to the work done by all the forces, net work done. So anyhow, you can solve this problem either through finding the acceleration and then finding the force and then solving it. This is also how you can do. Okay. There is one more method which is entirely not required here. What method is that? You got x as a function of time, and it will be helpful in very serious scenarios, in very complex scenarios, not for you right now. Okay? But I'll just mention because I mentioned the name. Here you got the force. Here you got the force. Now I needed to find the displacement, right? I needed to find the displacement. Rather than this, what I would have done, in case of variable forces, you find the force as a function of time. I'll just mention it here. Okay? It's just an extra point. Might be helpful in some very, very difficult problems where the force is a function of time. Okay? If x is a function of time and if you get force also as some another function of time, then what do? To find the work done, I do f dx, correct? Now you write f as a function of time, your force as a function of time. Let's write capital F dx. Dx will be from this differentiation. Okay? The force as a function of time and differentiate your dx. So dx will be f dash t, or the differentiation of f of t. It will be some function of time. And in this, it will be some g of t into dt. It will be like that. Okay? So you put it here, g of t and dt. This is how. So my point is, you differentiate the dx and get it as a function of dt and then put it here. And now whole of the integration is a function of time, so you can solve. This is only for very, very difficult problems where force and x both are function of time. ठीक है, just an extra point. All right, let's come back here. So which method do I prefer? Third method definitely not required here, but again it can be done. First method is getting the force, getting the acceleration. It's very selective method, not always applicable. Second method is the best one. So just mark key. We are going to find the delta k. If x is given, find the velocity, and then I straightforward get the work done. My favorite and most of the teachers' favorite method is the second one. All right, let's proceed further. Check. Now they are saying that a body of mass 3 kg is under the constant force which causes the displacement. Okay, all right, then again the similar kind of problem, displacement as a function of time. So either you can get the displacement in 2 seconds, that's also fine, and you can differentiate it to get the force, and then you can again get the work done by the force. But if you follow the second method, just like before, second method says कि you just differentiate this once, get the velocity. So the velocity will be 2t by 3. Getting the velocity and then get the change in kinetic energy, delta k. Get the point? So just follow this thing and again you will get the answer. We need not do the calculation for it, it's just the same problem. Check. Proceeding into the next part. So that was quite an intensive portion for your work done, calculating the work done, applying the work energy. I hope it was helpful. Let's proceed to the next one, and you guys need to just revise it and solve more problems. Check. Conservative forces and non-conservative forces. Again, a very good point regarding the assertion reasoning problems. Just a moment. Okay. So conservative forces are what forces? They are the forces in which the total mechanical energy remains conserved, and work done is independent of the path, because the potential energy is only defined in case of conservative, and it depends upon initial and final positions, not the path taken. Okay. Work done is independent of path and it depends upon initial and final position. The work done along a closed path is 0 because initial and final will be same, so work done is 0. It's generally central in nature. The conservative forces acts towards the center which is applying the force, like the gravitation force center of the earth. Total energy remains constant, total mechanical energy is constant. The work done is completely recoverable. That means in going forward, you get positive work, so going in reverse, you get the negative work, straightforward. Here the work done depends upon the path, non-conservative forces like the friction, the drag force and all other sort of forces. The work done along the closed path is not 0, definitely it depends upon the path. Forces are velocity dependent like the drag force, the viscous forces. So any force which depends upon the motion, the velocity, and such kind of forces are always non-conservative in nature and they are retarding in nature maximum times. The energy is dissipated at heat energy. The work cannot be recovered back. These are the conservative and non-conservative. Next part, again the very important one, total mechanical energy. So mechanical energy possessed by the body is divided into 2 parts, is classified into 2 parts. One is due to its position, which is the potential energy. So potential energy due to the position. We all know spring force depends upon how much you have stretched, what is the position of the object. Gravitational force also depends upon what's the position of the object from the surface of the earth or from the center of the earth. So it depends upon position. While the kinetic energy depends upon velocity due to the motion, due to the velocity. Okay? Alright. The mechanical energy classified into 2 parts. We'll discuss one by one, both of them. Firstly, the kinetic energy. Just looking at the formulas, the kinetic energy is half mv square. We all know this thing. Further, some more patterns or some more formats of this formula. I can write it as mv into v, and mv is what? Momentum. Half into momentum into velocity. Okay? Or I can also write it as p square by 2 into m. Multiply m and divide by m, so it becomes p square by 2m. These three formats you can use to quickly calculate the kinetic energy. Alright, let's see one question. When a momentum of the body is increased by 200%, that means the momentum becomes 200% more than the initial. So 2p plus p, it becomes 3 times. Take? It becomes 3 times, while you know ki the mass of the body is not going to change. So I'll suggest ki you relate it with this formula. K is p square by 2m. Using this formula, if you solve, because mass is not changing, velocity one I cannot write it because it's not going to give me the correct answer. So use this one. Okay? So let's find out if the momentum becomes 3 times, then the kinetic energy is going to become 9 times. Okay, square of this, so it becomes 9 times. So how much did it increase? Just subtract k from it. So k plus 8k. So it increased 8 times, that means 800 times. It increased by 800 times. Like this you have to do. They are asking not the final, they are asking just how much it changed, how much it increased. Alright, fine. Next one. Body kinetic energy twice its momentum, the speed. Okay, so it's the straightforward, not an issue. Just write the formula which we discussed in the starting. Half momentum into v. They're saying he has the kinetic energy twice its momentum. That means magnitude wise k is 2 times p. So I'll write it here. Cancel the p and p, cross multiply, so velocity will be 4. That's it, straightforward. 4 meter per second, not an issue. Next one. Potential energy. We discussed that mechanical energy is classified into 2 parts, kinetic and potential. Kinetic we just saw. We did some great problems on the kinetic energy. Now let's talk about something more, something about the potential energy. You all know the potential energy is the energy possessed by the system due to its configuration or due to its position. Okay? In the gravitation, I know ki as we raise the object above the surface of the earth or from the center of the earth, its potential energy is going to increase. Correct? In the spring, I know as I stretch the spring or if I compress the spring, in both cases the potential energy will increase. So that's how we check the potential energy. Okay, let's discuss some points about potential energy. Check. Potential energy, first of all, is only defined for conservative forces. What are conservative forces? We just saw the forces whose work doesn't depend upon path, the forces in which the total mechanical energy remains conserved, and they are central. Also, they might depend only on the position, not the velocity. So usually they depend upon the position, like the spring force, gravitational force, electrostatic force, they all kind of depend upon the position, the distance basically. So they say work done by a conservative force is minus of change in potential energy of the body. This thing you can keep in mind. What did I say? Work done by conservative force is minus of, that means it's the opposite scenario, the minus of change in potential energy. Using this, can you solve this one? Potential energy of the system increases if work done, let's say. If the potential energy is increasing, delta U will be positive, that means the work done by conservative force has to be negative. If the delta U positive means the change is positive, so potential energy is kind of increasing. Delta U positive means potential energy is increasing, right? So they are saying ki if work is upon the system by a non-conservative force, no, not at all. We are not discussing non-conservative. Work done by the system against a conservative force, Work done by the system against a non-conservative force? No. Work done upon the system by a conservative force. Acha. So let's analyze these statements, ki how they are different. The second one and the last one. We found that work done by conservative force is negative. That means the conservative force is doing negative work. That means the system is doing work. Okay? So who is doing the work? The system. Is the conservative force doing the work? Work done by the conservative force? No. Since the work done by conservative force came out to be negative, so actually the conservative force is not doing work. Who is doing? The system is probably doing the work. This is how we decide. Next one. So that was quite a good one. Okay. Alright. So they have said ki there is a rod of length L. Okay. I write it L here. Okay. L, the dimension wise. Check it. Mass is there M and the length is there L. It is pivoted at one end and is placed to angle theta, the increase in potential energy. Remember that in case of extended bodies, extended objects, that means rigid bodies, big objects, you need to remember you can find the potential energy using the MGH formula. Using the MGH formula by applying it on the center of mass. Using the center of mass. Okay? So I know that in case of gravity, the gravitational potential energy, if I write the change in potential energy, depending upon are we going upwards or are we going downwards, is plus minus mgh. So m is the total mass and this h will be the displacement of center of mass. The displacement of center of mass. So now tell me, is the center of mass rising upwards? Here at the point L by 2 we have the center of mass. Did it go upwards? This is L by 2 now and this is the center of mass. Yes, it definitely went upwards. How much did it go upwards? And now it's the pure trigonometry. Okay, let's find it out. Okay, how much is this displacement? So this was L by 2 and if I say this is also L by 2, so can I find this distance? Yes, I can find this distance. It will be L by 2 cos theta. L by 2 cos of angle theta, because this is the angle theta. L by 2 cos theta. Total was L by 2 and this is L by 2 cos theta. So H is what? H is L by 2 minus L by 2 cos of angle theta. And let's put it here. And if it is going up, the potential energy is increasing. Correct or not? The potential energy is increasing as we go up. So it is plus mg and instead of h I will write L by 2 1 minus cos of angle theta. So which one is it? Mg L by 2 1 minus cos of angle theta. And it's a very standard problem. You will see it many places. Next. Particle is released from height s from the surface of the earth. Great. From the surface of the earth, the particle was at height s. Check. S height it was, and it was falling freely under the gravity. At a certain height, its kinetic energy is 3 times its potential energy. Check. 3 times its potential energy. Now first of all, I need to remember that the total mechanical energy is the sum of kinetic energy plus potential energy, and in case of gravitation or conservative force, it should remain conserved. Okay? Because there is no drag force, there is no friction force, so the total mechanical energy will be conserved, so the sum of kinetic and potential will remain conserved. That means at the topmost point we had released it. So initial kinetic energy was 0. Initial kinetic energy was 0, and if I can get the reference potential energy at the surface as 0, so that means the initial potential energy at a height h above the surface will be mgs. Correct or not? So that is the total potential energy. If I do the sum, so initially the total energy would have been the sum of these two. That means mgs. Get it? So the total potential energy will always remain mg into s. Whether the kinetic energy is increasing and the potential is decreasing doesn't matter. Now what did they say? At certain height, let's say it was falling downwards, it was coming from here and it went down and it reached a point which was at a height h above the surface of the earth. I know key potential energy would have been mgh, correct? Potential energy would be mgh. Check. As the reference ground is 0. They are saying ki kinetic energy is 3 times the potential energy. So at this particular height, where we have to find the height, I am writing the kinetic, which is 3 times its potential. So 3 mgh, correct or not? Now what will be the total energy? The sum of these two. Mgh plus 3 mgh is 4 mgh. And I know ki total energy will be conserved. So 4 mgh will be equals to mg s. M to M cancel, G to G gets cancelled, so H is equals to S by 4. Now they are asking ki the height from the surface of the earth. We just found ki it is S by 4. And the speed of the particle respectively at that height. Okay. So from the relation that kinetic energy is 3 times the potential energy, we can figure out this problem, the velocity problem. Okay, let's check it. So I'll write kinetic energy half mv square 3 times the potential energy mg, and h height is s by 4. M gets cancelled, 2 and this 4, the 2 is remaining. Now take the under root of the whole equation. So here on the LHS we get v, and on the RHS we get under root of the whole expression 3g s divided by 2. So that will be the velocity. Under root, whole should be inside the under root. So the A option. Get it? Check the options. The height is s by 4, great. And the velocity will be under root of this complete expression, A option. This is how you guys need to solve the work energy problems. Alright, let's proceed further. Potential energy in case of the spring. So you know that key, if there is a spring constant is k, there is an object, not an issue. What is the mass? If we stretch the spring or we compress the spring by s, by any x displacement, the potential energy will be half kx square, straightforward. And if they ask us about the work done by spring force, you will always write minus of change in potential energy, which is minus half k x final square minus x initial square, with a minus sign here. Remember this thing. That's how we'll use the work done by spring force. Let's take one problem. They are saying two springs A and B having constant Ka and Kb. So in the ratio 1:2, Kb is 1 and Ka is twice. Stress by applying a force of equal magnitude. Great. So the force, I know the spring force is written as minus Kx, and it's always opposite to the displacement, so that's the minus sign, but it will be proportional to x. They are saying ki what is the x? Okay, force is same, Fa is equals to Fb, so Ka into Xa, Kb into Xb. Ka is twice of Kb, so I'll write twice of Kb, and Xa, and it is Kb into Xb. Kb gets cancelled. So the stretch or the extension in the second spring is twice the extension in the first spring, because second spring constant is lesser, so its extension will be more. The energy stored in the spring A is Ea than the energy stored in the spring B. So I'll write Ea as half Ka Xa square, and that is Ea, and Eb will be half. Kb will be written as Ka by 2 from here, so Ka by 2, and Xb will be written as twice of Xa, so twice of Xa whole square. So it will be 1 by 2. I'll keep the 1 by 2 outside only, and Ka I'll pull outside, and Xa square I'll pull outside, and here I'll get 4 in the numerator and 2 in the denominator. Check. Half Ka Xa square is Ea. That's how you simplify. So it is EA by 2. So EB will be simply EA by 2. Just follow the correct method, properly write it, and you will get the answer. Don't rush. Check. Next one. The potential energy of a long spring when stretched by 2 centimeters is U. Again the similar problem. The spring is stretched by 8 centimeters, the potential energy will be. I know ki potential energy is proportional to x square. That's it. So if the extension is 4 times quadrupled, 2 into 4, 8, it has become 4 times, the potential energy will become 16 times. That's it. 16 times. Easy one. Okay. Now the conservation of mechanical energy. So we saw that if only conservative forces are acting, the total mechanical energy remains conserved. So you can write down only if or only the conservative forces are acting, then total mechanical energy remains conserved. Then total mechanical energy remains conserved. That means ki if the friction and drag forces are absent, then the total mechanical energy remains conserved. That's it. Conserved. Okay. So you can apply the conservation of mechanical energy, that the total initial mechanical energy is total final mechanical energy, which is the sum of initial kinetic plus initial potential, final kinetic plus final potential. Okay. Let's see some problems based upon this. Now, a block of mass m moving with velocity v naught on a smooth horizontal surface hits a spring of spring constant k as shown, the maximum compression in the spring. Using the conservation of energy, we have to solve it. Okay, just be patient. Such questions are very, very easy. You can easily solve them. Just apply that previous equation. Okay. For that you must know ki what is initial and what is final. So I'll write it here ki what are the initial parameters. So initial kinetic energy will be based upon the velocity given, half mv naught square. Okay. As soon as it strikes the spring, its velocity will be half mv naught square, and as soon as it comes in contact, the initial compression or extension has to be 0 because nothing was there before. So initial potential energy I am writing 0. Finally what they are saying, you need to carefully and smartly analyze what is happening finally. The maximum compression. Now what is maximum compression? Maximum compression means कि the block pushes against the spring, it compresses the spring, and that's it. Cannot go any further. Cannot go any further means the velocity at that point becomes 0. So you can always mention at the maximum compression, the final velocity becomes 0, or the final kinetic has to become 0. So K final will be 0 and U final will be half K x square, which is the maximum extension. Now apply your energy conservation. So conservation of energy principle says ki initial sum of kinetic initial half mv naught square and potential initial will be equals to kinetic final and potential final. Check. Half gets cancelled, and here I can easily get the maximum compression will be under root m by k into v naught. Just cross multiply this thing, cancel the half and half, and you get the answer. Okay, like this. Take the k here, you will get the answer. This is how conservation of mechanical energy is utilized. Check. One more similar problem. They are saying ki, sorry, very bad noise. All right, leave it. Initially the mass m is held such that the spring is relaxed, so there is no extension or compression in the spring initially. So u initial was 0, and now what they are saying, ki we release it. Okay, we release it, and they are asking ki what is the maximum elongation in the spring. Maximum elongation again means ki it's going down and its final velocity becomes 0, while I know ki initial velocity was also 0. This was potential energy. ठीक है, u is potential energy. So spring potential energy I know, but what about gravity? Because it is hanging vertically, so gravity is also there. So just mark a point, gravity is also there. So potential energy will include gravity also this time. ठीक है. Now just see that as I go down, let's say the maximum extension is some x max, it is going down, to gravitational potential energy is decreasing. So if I say ki the final potential energy due to gravity is 0, the initial will be mgx. So I'll write it here, u initial due to gravity, u initial due to spring, k initial, u final due to gravity, u final due to spring, k final. ठीक है. U initial due to gravity will be mgx because it was x height above this final. Let's say it's the bottommost position, the bottommost position, so above this, plus 0 is equals to final. I say the bottommost position, the gravitational potential is 0. I can always take any reference, so gravitational potential I took here as 0. Finally, spring potential is half k x maximum square, and final kinetic is definitely 0. So from here you can just cross multiply. X is not 0, I can skip it, and I'll write that ki x I'll take out, and it is half k x max minus mg is 0. X max is not 0 because we are not looking at initial position, so x max becomes 2 mg by k, standard format, 2 mg by k. Remember this thing. Okay, we released it from natural length. Okay, next thing is equilibrium. Okay, what is equilibrium? The mechanical or translational equilibrium refers to the situation when the net force is 0 or its potential energy is minimum. So if we say that ki at equilibrium the potential energy has to be minimum, that means it's a condition of minima, du by dr is 0. Also I know that f is minus du by dr, correct or not? This implies ki f is also 0, that we already know ki at equilibrium the net force is 0. Okay, this is how we get the condition of equilibrium, that du by dr is 0. Let's check out some important problems here. Check. Potential energy of a particle moving along x-axis is given by ux is ax minus bx square. Find the equilibrium position. That means the position x where f net is 0, or I can say potential energy is minimum. Both the things should be happening at equilibrium. So just differentiate it and make it 0. So du by dr is 0. Easy step. So whenever you see equilibrium position and you see the equation of u, differentiate it, equate it to 0. Standard process. So differentiating ax will be a minus bx square is 2bx is equals to 0. So x is a by 2b. That's it. So easy, is it or not? So just remember the condition कि at equilibrium you need to differentiate the potential energy with respect to position or distance. Check. That was about the potential energy and the kinetic energy. I said that work is done by the force and then this work can be transferred to energy, but how fast it is done, or we have to do the work We have to do the work, but how much time it's taking to do the work, or is it doing the work slowly, or is it doing the work faster? So for that, or for this aspect, we introduce the concept of power. So what is power? Power is defined as a rate of doing work, or rate at which the energy is spent. ठीक है? Average power, if I say, comes out to be force into velocity. If you know the instantaneous force and you know the velocity, if you know the force and the velocity, then you just do the dot product when the force is constant, and when I don't know if the force is constant, then you just write the total work done upon the total time taken. That's how you get the average power. Check. Also, sometimes they ask the instantaneous power, which is always straightforward. So instantaneous power is also the same as when the force is constant. So at a particular instant, I just need to see what's the instantaneous value of the force and what's the velocity, and we can solve it using this. Let's take one question. If a force of 9 newtons is acting on a body, then find the instantaneous power supplied by the body when its velocity was 5. Correct or not? So instantaneous power is simply the force at that moment, 9 newtons. And they are saying that velocity and force are in the same direction. So dot product will be maximum. Cos theta will be 1. So 9 into 5, 45. And watts. That is it. This is how you do the problems on the power. Another one, and here they have mentioned the velocity and the force in terms of dot product. So to obtain the power, just do the dot product. In the dot product, I know that I multiply the I together, so 5 into 2, J together, 2 into 5, and K together, minus and minus, plus 10. So it will be 10, 10 and 10, 30 watts. Okay, straightforward. This is how you solve the problems on power. Again, kind of very easy. Next is your vertical circular motion, and for this, most of you would understand the aspects of circular motion. Ki what are the acceleration and what are the parameters omega of the circular motion. So in the end, we are going to brush up those concepts as well. Right now, let's look at the vertical circular motion. So in the vertical circular motion, what happens? Ki let's suppose there is a scenario, we have a string and a little particle, kind of a pendulum, is suspended from this string, and which can be flicked or which can be provided momentum, so it can turn about a center of this circle and it will move in a vertical circular motion. So what velocity should be given? What velocity should be given at the bottommost point so that it can complete the vertical circular motion? And suppose the velocity is not sufficient. So what can happen? If the velocity is more, then what can happen? These are the various scenarios which you have to analyze in the problems. Keeping in mind what equations do we follow? So first thing is, you need to use work energy principle or conservation of energy. Conservation of energy. Second, you need to use Newton's law along the string in the central direction using the centripetal force. Using centripetal acceleration, apply Newton's law. Apply Newton's law along the string in the central direction, and that's how we can solve the problems related to vertical circular motion. Now see, in this there is a very standard result कि if a string pendulum is there, for a pendulum, the minimum velocity at the bottommost point the minimum velocity should be under root 5 gr, and in this case, okay, in this case it will complete the vertical circle. Okay. If it completes the vertical circle, then at the topmost point the velocity doesn't become 0, the tension becomes 0, and the velocity at the topmost point the minimum velocity at the topmost point comes out to be under root gr. Okay. For the scenario, it completes the vertical circle and then the tension is going to be 0. So this is the scenario of your vertical circular motion. Let's just quickly take an example and then we'll wind up the session. Okay. So let's suppose this is the scenario here. Key at the bottommost point, we give it some velocity. And if I look at the tension here, how do we write the tension? So see, in the direction of the string, there is tension and there is this mg force. So I'll write the equation, tension minus mg is m into centripetal acceleration, which is mv square by r. At the bottommost point, it works. Now suppose ki it goes to the position B. Now in the position B, let's say this is the position A. Okay, velocity at A. In the position B, its velocity can be upwards, can be 0, can be anything. Okay. mg would be vertically downwards. So at the point B, if I write the forces, then it will be just that Tb is equals to mvb square by r, because there is no other force in this horizontal direction. That's how we discuss the vertical circular motion. The problem they are saying ki a body initially at rest sliding along a frictionless track from the height h as shown in the figure just completes a vertical circle of diameter AB, which is equals to d. Now see, here straightforward concept is, if you release an object from height h, at the bottom of this path, the velocity it gains at this point due to this height will be under root 2gh. And then it moves in a circular motion, completes the vertical circle of radius r is equals to d by 2. So its velocity at the bottommost point must also be equals to under root 5 gr of this radius of the circle, and they both must be equal. It gains the velocity under root 2gh, moves in the vertical circle with the velocity under root 5 gr. We equate both of them and then we'll get the relation of this height h. So under root 2gh is equals to under root 5g and r is d by 2. Square both the sides and g gets cancelled. So 2h is equals to 5d by 2, or h is equals to 5d by 4. Okay. 5d by 4. So this was your vertical circular motion, and similar problems are always asked from the vertical circular motion. I think you guys can revise it properly now, since you have covered almost the major concepts and the major points of this chapter. Just solve some problems and you are good to go with the chapter vertical circular motion. Alright, let's take this one. It's again the similar. What's the difference in this problem and the previous one? Just the path, nothing else. So path can be anything. Path can be anything. You just need to check the vertical height, and same thing will happen here. The under root 2gh velocity, and it should be balanced by under root 5gr. Same thing. Check it. Straightforward problem. Alright, the last part, the important aspects of circular motion. So in the circular motion, I know that whenever a body rotates in a circle, what are the accelerations and what is the relation between the acceleration? If it is a uniform circular motion, the speed must remain constant. the speed is constant, the angular velocity must remain constant. And if that is the case, then how do we write the acceleration? The centripetal acceleration will be written as v square by r, or omega square r, or omega into v. This is how you write the centripetal acceleration. If it's a non-uniform motion, then there will be another acceleration, which is tangential acceleration and angular acceleration. Okay? And those things you guys are going to discuss in the chapter of rotational dynamics, rotational motion. So for this chapter, we have covered most of the important concepts of work energy and the applications of work energy in the circular motion, in the vertical circular motion. Now you guys just need to practice more problems and just stay tuned with more videos of such kind of short series where we'll revise some more concepts. And again, as usual, all the best for your exams. Keep practicing more problems.